In the last video, we have already discussed the theory part of data standardization. Now let's go through the code. Okay, so here what we are doing, we are initially importing all the required libraries like NumPy, Pandas, Matplotlib, and then Seaborn. Seaborn is a library that is built on top of Matplotlib. Okay, and then what we are doing over here, we are reading this social network ads.csv. Okay, so if we observe this particular social network ads.csv, there is user ID and then gender, and then we have age, estimated salary, and the last column is purchased. But in all these columns, we are interested in only age, estimated salary, and purchased. So that's why here, if we observe, we are keeping use calls equal to 2, 3, 4. That means second indexed column, that is 0, 1, and 2, that is age, and then estimated salary, and then purchase. So these three columns we are selecting out of the existing CSV file. Okay. And if we observe this DF, what we are having? We are having only the age, estimated salary, and purchased. So here, if we observe, age is in some scale of like it will be maybe from 0 to 100 or 150 at max. Okay. And when it comes to estimated salary, it will be something from 10,000 to maybe it can go up to 1 lakh. So these are two different scales, like completely different scales. So on this, we can apply any of the scaling techniques. So in the previous videos, we have already discussed about data normalization. Okay. And also we have discussed about the problems with it. So if you have missed out on that, you can check it out. Now, like in standardization, what is our main idea? Our main idea is to make the mean to 0 and standard deviation to 1. So how we will be doing that? We'll be taking this age column into consideration and we'll be calculating the mean of all these points. What is that? That is the average of all these points. So as here 400 points are there, if we are considering whole of this data as our training data set, then we'll be taking all these 400 points into consideration and then we'll be calculating the average. And also similarly, along with the average, we'll also be calculating the standard deviation. So this age column will be having some mean and standard deviation. Similarly, how we calculated for age, in the same manner, in this column, we'll be calculating the mean for estimated salary and standard deviation for estimated salary. So now we have individually like mean and standard deviation of age and mean and standard deviation of estimated salary. And then if you guys remember, what is the formula for that? The formula looks something like this: xi minus mu by standard deviation. So this formula we'll be applying. So how, like on which points we'll be applying? We'll be taking each of these points. Like here we are taking this particular 19. On 19 we'll apply the formula 19 minus uh, average age divided by standard deviation of age. Like that we'll be applying on each of these points and we'll be changing these data points. So that is what we'll be doing. And similarly in the estimated salary, 19,000 minus like average estimated salary divided by standard deviation of estimated salary. So like that, on this point we'll be applying, and this point and this point, like that, whole data set will be changing. Okay. So in order to get some clear idea, I'm explaining this. So now let's move on to the next part. So we can have something like hist plot, and hist plot, what we'll be having, we'll be having the count of data points that are occurring within that particular range. So there are these many number of people we can say in the whole data set with the age of 40. Like that, it will be signifying. And there is a KDE plot as well, which is a smooth approximation of this, which represents the density of points. So individually, we can see the KDE plot as well. So here, if you observe, we are having individual KDE plot with respect to the age. So this is the corresponding KDE plot for the age. And similarly, we are having other column, right? Estimated salary. On that also, we can observe the same. So our estimated salary is ranging from somewhere from, you can think like 15,000 to 1,50,000. By seeing this, we can understand. And similarly, age is ranging somewhere from 7, or like by his plot, we'll get even clearer either. Maybe something from 15 to 60, it is ranging. Okay. So, and this is the corresponding KDE plot of the estimated salary. So if you wanted to observe the scatter plot, uh, on x-axis we are taking the age, and on y-axis we are taking the estimated salary, and on the output column we wanted to like show some division with the help of color. That's why we are giving it in hue, and then we are mentioning the color using this palette. So for 0 class we are mentioning it with black, and for 1 class we are mentioning it with red. So we can say like we can draw some line kind of this over here. And we can say all the points on this side of the line. Like let's say if you're drawing line like this, then to this side of the line, most of the points are of zero, and to the other side of the line, most of the points are one. So like that we can like maybe classify this. Okay. But for classification, we'll not be using directly this linear regression. We'll be seeing in the next videos how we'll be doing some classification problem. Okay. So here if you observe, before going on to like applying this particular data standardization, we are splitting the data. And how we are splitting? We are taking the testing size to be 0.25. That means 25% of the points will be in the testing data set, whereas the remaining 75% of the points will be lying in the training data set. So in train, we are having 300 points, whereas in test, we are having 100 points. Okay. And similarly, Y-train and Y-test will be having the corresponding outputs. So in order to apply standardization, we can simply use standard scalar. And if you guys remember, in order to apply normalization, what we have used? We have used something called as min-max scalar. Okay. So scalar dot fit, and fit always will be applied on training data. This we have already discussed in the previous videos as well. And then we'll be applying the transform on the like both training data and also the testing data. And if you wanted to observe the mean, like this is the mean for age, whereas this is the mean for salary. Like we can get the mean that is calculated on the training data. Okay. And if you observe describe, it will be showing the minimum value, maximum value, mean value, 25th percentile, 50th percentile, 70th percentile, all these values it will be giving. So here, what are the values in which we are very interested in? So mainly we are interested in observing the mean and standard deviation, whereas in case of normalization, we are interested in observing min and max. Okay. So if you observe the mean of age column is around 37.68 and standard deviation of it is 10.79. And similarly, mean of estimated salary is something 69,000 something, whereas standard deviation is 33,000 something. Okay. So now what is our objective with the help of with respect to data standardization? We'll try to make this mean to zero and standard deviation to one. Okay. So let's see in the X train normalized. So like our scaled data is stored in X train normalized and X test normalized, right? So let's see the describe on it. So if we check the describe on X train normalized, we are having a mean of zero and standard deviation of one. Okay. Basically, it is 0.00000, some very small value. So here we are rounding it to 1. That's why it is showing in minus. So you can think it as 0. So that we are doing it to 0 and standard deviation we are doing it to 1. Whereas in case of estimated salary, it is exactly made to 0 and the corresponding standard deviation is made to 1. Okay. And if we check the X test, on X test, we are having a mean of 37 and standard deviation of 9.5. And for this, the mean is 70,310 and standard deviation is 36,210. So on X test scale, the mean and standard deviation, we expect it to be 0 and 1, but it can happen that it might be slightly deviating from 0 and 1. Okay. Why is that? Because we are not showing this testing data to the corresponding standard scalar, or like here we are having this function, right? In this function, we are in fit, we are only passing training data. That means we are only showing the training data to this standardization function. We are not showing our testing data. That's why it can't handle or it cannot make the mean to exact zero and standard deviation to exact one. So let's see what are the mean and standard deviation after applying this particular standardization. So if you observe, here for age, it is perfectly giving 0, and standard deviation is not exactly 1, it is 0.9. Whereas for the estimated salary, the mean is 0 and standard deviation is 1.1. Like that, there might be some slight deviation as we are not showing the complete testing data to the model. Okay. And now, before and after scaling, if you observe the data distribution will exactly look the same, but only thing that differs is the scale. So previously, it is the age scale that is from 20 to around 60, and similarly, this is the salary scale, which is ranging from 20,000 to 1,40,000. Whereas after scaling, both are in range of some -2 to +2. Okay, and here also it is in the range of -2 to +2. So, like, why is this -2 to +2? Let's try to understand that. Basically, on applying this, it is making the mean to 0 and standard deviation to 1, which means it will follow something called as standard normal distribution. Okay. And how will the graph of standard normal distribution will look like? It will look something like this. Okay. So in this is the mu. That means most of the points will be lying at mu. And from mu with a standard deviation of 1, that is, like, let's say here we are having -1 and here we are having +1. Okay. And if we write -2 and then we are having +2. Okay. And then -3 and then +3. So I think you guys know about, have a little bit idea about the standard normal distribution. In that, the graph will look something like this. So between -1 and +1, almost 68% of the points will be lying. Okay. And between -2 and +2, we'll be having some 95% of the points. Whereas between -3 and +3, almost all the points, like 99 point some percent of the points will be having. Okay. So like that data distribution will be there after applying this data standardization. Okay. So like most of the points will be lying in this region, that is between -1 and +1. Okay. And 95% of the points we can say that those will be covered between -2 and +2. And almost 100% of the points will be covering between -3 and +3. So like this, the data is distributed. Distribution looking exactly the same, only the scale is differing. And now let's try to observe the KD plot. So here, if we observe, this is before scaling. These are the KD plots. So here, if you observe, there is a blue single line and there is some orange line. So this blue line is signifying about the KD plot of age, whereas this orange line is signifying about KD plot of salary. And why are these like this? That is because these scales are completely different, right? As these are completely different, we can't plot them on single graph. If we plot them, it will look something like this only because A scale is very small. It will be ranging something in between 20 to 60 or 15 to 60, whereas salary is in the scale of 20,000 to 1,40,000, which is very big when compared to age. That's why the plots are not clearly visible over here. If you wanted to look into clear plot of this, we might do something like zooming in and observe this individually, and maybe zoom in over here and observe this individually. Like that we can do in order to observe the exact KD plot. But after scaling, if we apply this particular, or if we draw this particular KD plots on the same graph, it will look something like this because now both are in same scale. That's why we are able to show both of them in same graph. Okay. So individually, if you observe, this is the KD plot of age before scaling, and this is the KD plot of age after scaling. And similarly, this is the KD plot of salary before scaling, and this is the KD plot of salary after scaling. Okay, this is regarding the testing data. So till now, all these KD plots are corresponding to training data. Whereas if you wanted to check the same with testing data, so on testing data also these look like that only before scaling, but after scaling, we can see both at a time. Okay, so this blue one is corresponding to age, whereas this orange one is corresponding to salary. So I hope this notebook is clear for you. And if you have any kind of doubts, you can comment down in the comment section. And that's it for this video. And thank you everyone. Bye bye.